All right, we have a bug with a very small mass, 0.02 kilograms. It's at rest on the edge of this disc. The mass of the disc is 0.1 kilograms. The radius is 0.1 meters. So we know the bug is 0.1 meter away from the axis of rotation. And this is rotating around a horizontal plane around this vertical axis through the center. They give us the initial angular velocity, and they also give us the moment of inertia of the disk, so we don't have to calculate that. So what's going to happen here is the situation we have, this is our initial situation, and then the bug crawls to the center of the disk, and we want to see how that changes our momentum. Now, in this situation, we know that the angular momentum is conserved because we have no external torque working on the bug and disk system. The initial moment of inertia, then, is going to be the inertia of the disk plus the inertia of the bug. Now, again, the inertia of the disk is given. That's 5 times 10 to the negative 4th kilograms times meter squared. Plus, well, let's take a look at this bug. Okay, this bug right now is a point mass. And so if you remember, for a point mass, it is going to be I equals mr squared. So for this situation, the mass of the bug is 0.02 kilograms. And the radius that it is at is going to be 0.1 meters quantity squared. So what happens is when we plug and chug all that in, we get 7 times 10 to the negative 4th kilograms times meter squared. So this is our initial moment of inertia of the system. So then what happens is the bug crawls in and the bug reaches the center here. Now if the bug is at the center, right, if we're looking at the point mass of the bug, remember that's equal to mr squared. But r is 0 meters if it's at the center, which means the inertia of the bug has to also be 0. So it turns out that the final moment of inertia is only the moment of inertia of the disk, which is 5 times 10 to the negative 4th kilograms times meter squared. Now, if we take a look and compare the two, we have 0.0007 and we have 0.0005. So we started with more than we ended with. So if we're looking at the new angular velocity, since our moment of inertia went down, it should turn out that our new angular velocity goes up. So let's take a look. We know that the angular velocity initial has to equal the final angular velocity. So we have I initial omega initial equals I final omega final, and we're looking for this final angular velocity. The initial is 7 times 10 to the negative 4th kilograms times meter squared. The initial speed, they tell us, was 10 radians per second. 10 radians per second. And that equals 5 times 10 to the negative 4th kilograms times meter squared times the final angular velocity. So all we need to do here is divide, and it turns out that that final angular velocity is 14 radians per second. And that's great to see since we started at 10 and we knew that it should be increasing. So now we want to talk about the change in kinetic energy of the system. So from our other examples, remember when we derived the equations for kinetic energy in terms of momentum, and we have a constant momentum because it's conserved, we know that it's a direct relationship. So so if the angular speed increases, we know that the kinetic energy must also be increasing. Or likewise, we know it's an inverse relationship with momentum. Since our momentum decreased, we know that our kinetic energy is increasing. So let's take a look at the two. The final kinetic energy is 1/2 I final omega final squared, which is 1/2 5 times 10 to the negative 4th kilograms times meter squared times 14 radians per second squared, and that ends up being 0.049 joules. Now our initial kinetic energy was 1/2 I initial omega initial squared. That's 1/2 7 times 10 to the negative 4th kilograms times meter squared our initial velocity was 10 radians per second. We want to square that velocity, and then we end up with 0.035. So if we're looking for the change in kinetic energy, remember that's K final minus K initial. So that's 0.049 joules minus 0.035 joules. And so then we end up, for that change in kinetic energy, a positive 0.014 joules. Now, obviously, we're not looking at a huge amount of change here because our bug's pretty small. So any work that's being done for it to walk from the outside to the center is going to be a small amount of work, so that transfer of energy is not going to be quite as big either. Okay, so let's take a look at another situation. So now bug is in the center, and now it wants to walk to the outer edge of the disk, and they want to know what the angular velocity of the disk is, right? Well, here's the thing. If it's walking back out to the outer edge, and I want to know the angular velocity, right, whatever work that it gained, it is going to lose moving in the opposite direction, right? So when all is said and done, if it's in the same position, right, same disk, moment of inertia is the same, what's going to happen is the angular speed is going to go back to 10 radians per second. Okay, so it's going back to the original value. So if it crawls back, so the gain in energy from the bug to center is equal to the loss in energy from the center back to original position. All right, so what would happen then is we would end up with that same angular velocity. So what's the new kinetic energy of the system? Okay, well, that new kinetic energy, we did gain 0.049, right? So we gained 0.014, and we went from this initial kinetic energy to this final. We're going to go back to the initial kinetic energy. So the new kinetic energy is going to be 0.035 joules. So it's back to the original. Okay, so again, what is the cause of the increase and the decrease? And this is the bug adds and loses energy by the work done crawling from the outside to inside and back. Okay, so the bug is just going to add energy as it walks to the center. It's going to lose energy as it walks back to the edge of the disk.